Hi, my name is Sean Kavanagh. I'm a PhD student in the groups of David Scanlon at UCL and Aaron Walsh at Imperial. My research is focused on solid-state photovoltaic materials. In this presentation, I'm going to speak about our work on defect in cadmium telluride, specifically focused on the surprisingly complex cadmium vacancies. So let's get into it. Cadmium telluride is a key photovoltaic material, being in fact the first thin-film photovoltaic absorber to achieve commercialization. Efficiencies are still well below the detailed balance limit of 32%, however, with a current record performance of 22% by First Solar. Cadmium vacancies have long been known to be an important acceptor species in commercial cadmium telluride, which is typically grown under tellurium-rich p-type conditions, favoring the formation of these defects. That said, the specific atomistic processes by which they affect device performance, such as conductivity and recombination, have remained unclear. As such, we applied a comprehensive analysis of this defect species under a high level of theory in order to elucidate its behavior at the atomic level and to reconcile theoretical predictions with experimental observations. Starting from the bulk material, we can think of what happens when we remove a cadmium atom. And this way of understanding defect behavior was pioneered by G.D. Watkins in the 1980s. So it takes its two valence electrons with it, coming from the top of our VBM, which is primarily composed of tellurium p states. In the fully ionized -2 charge state, there are no missing electrons, and so we retain the tetrahedral symmetry of, um, of the cadmium site with a slight contraction of the neighboring tellurium atoms and an overall shallow delocalized defect state. In the singly charged state, the 5/6 partial occupancy of the triply degenerate tellurium p level at the VBM has a Jahn-Teller instability, and so we distort to a trigonal symmetry defect with one tellurium atom moving away from the vacancy. So this results in a localized whole polaron on this tellurium atom here with distinct p character. So while theory has long struggled to find this localized solution for the minus charge vacancy, it was actually identified experimentally back in the 1990s by Emanuelson et al. Using photoelectron spin resonance. So having an unpaired electron, this defect species is paramagnetic, allowing it to be readily identified by spin resonance techniques. They furthered this analysis by shining light at controlled wavelength on their sample and monitoring the ESR spin resonance signal intensity as a function of the input photon energy, a technique known as photo-ESR. They found that with photon energies greater than 0.47 electron volts, the spin signal intensity decreased, which they deemed to be the result of an optical excitation of an electron from the VBM to the defect level, resulting in the -2 charge vacancy with a hole left behind at the VBM. Using state-of-the-art computational techniques, we can in fact predict the spectroscopic signatures of these defects, once we know their correct atomic structures, calculating the optical transition energies, the vibrational broadening, shown here, the vibrational relaxation or Jahn-Teller energies, and of course the thermodynamic charge transition energies. This provides us a powerful tool to directly compare with and validate against experiment, as well as directly connecting the nanoscopic defect picture to the macroscopic behavior. If we now turn our focus to the neutral vacancy, which initially has two holes in the tellurium P VBM levels, we see that there are a couple of possibilities. Two obvious solutions would be either a shallow defect where tetrahedral symmetry is maintained and the holes are essentially delocalized across the VBM. And this is in fact the structure which has been suggested by the majority of previous theoretical works. Alternatively, we could have a two-hole polaron arrangement, which is essentially just a doubled version of the whole polaron for the -1 charge vacancy. What we found in our investigations, however, was that a deep twofold C2V symmetry distortion can occur in which a strong tellurium-tellurium dimer bond is formed, producing a bonding state deep in the valence band and an antibonding state just above the conduction band edge. Similar metal-metal dimer reconstructions have been noted for anion vacancies in other 2,6 semiconductors like zinc selenide and zinc sulfide, but not for cation vacancies, which is partly why it took over 30 years of theory investigations of defects in cadmium telluride to identify it. In this case, the metalloid character of our anion, tellurium, allows it to undergo this somewhat unusual or unexpected dimer formation. This dimer state is much lower in energy than the tetrahedral or bipolar on solutions, and this drastically affects both the thermodynamic and, as you see in a second, electronic behavior of this defect species. Looking at our defect transition level diagram, we see that the identification of the tellurium-tellurium dimer state changes the picture from cadmium vacancies having two shallow defect transition levels at or near the VBM to, in fact, having a single deep negative U double acceptor level at around 0.4 electron volts above the VBM. One of the main difficulties in finding this species arises from the metastability of the other atomic arrangements mentioned earlier for the neutral vacancy, so the tetrahedral and bipolar states. Indeed, mapping out the potential energy surface between these configurations, we do indeed find a barrier of around 0.3 electron volts between these states. In fact, this is a general issue in computational defect studies where ground state configurations can be missed, as local structure optimizers can get stuck in these local minima, missing out on the true global minimum or ground state. There are a few strategies to deal with this behavior, such as deliberate distortion or fake atomic substitutions. However, these typically require either prior knowledge or a great deal of manual researcher effort, both of which can impede the throughput and predictability of ab initio modeling. So this is something we are currently working on improving to develop a general automated strategy to capture this deep reconstruction behavior. So watch this space. So the main event of the evening. To analyze the electron hole recombination kinetics at defects, we first map out the potential energy surface between the structures of the defect in its different charge states. From this, we can determine the classical energy barrier to the charge capture transition, represented by delta E here, as well as solving the 1D Schrodinger equation to obtain effective vibrational frequencies and calculating the electron-phonon coupling, all of which contribute to our final charge carrier capture rate. Firstly, we note the enormous difference in the potential energy surfaces for the -1 to 0 charge transition, depending on the atomic configuration for the neutral defect, i.e. whether you use the dimer structure or the bipolaron structure, which highlights the importance of getting the correct ground state defect configuration. We also note that anharmonicity in the potential energy surfaces plays an important role here. For example, we find this Morse-like potential for the neutral dimer state due to the presence of the tellurium-tellurium dimer bond. And so the commonly used harmonic approximation is not suitable in this case either. So transitioning between the tellurium-tellurium dimer neutral ground state and the -1 charged vacancy, we find a very small energy barrier for electron capture, so delta En here, but a very large barrier for hole capture going in the opposite direction, so from the -1 to the neutral state. Looking at the -1 and bipolaron, neutral bipolaron transition, we witness inverse behavior. So a tiny energy barrier for hole capture into the neutral bipolaron state, but a large barrier to electron capture from the neutral bipolaron to the -1 charge vacancy. Overall, we find that no single charge transition for the cadmium vacancy exhibits rapid capture for both electrons and holes. So under the standard picture, the Shockley-Reed-Hall model of a single defect level in the band gap, we would predict that the cadmium vacancies would be a benign defect species with negligible carrier capture. Instead, by including the possibility of the -1 to neutral dimer, the -1 to neutral bipolaron, and the bipolaron to dimer transitions, we in fact find a rapid electron hole recombination pathway, whereby the -1 charge vacancy effectively captures a hole with a tiny energy barrier um, to transition to the metastable bipolaron arrangement for the neutral vacancy, which then relaxes to the tellurium dimer ground state before capturing an electron, again with a very small energy barrier, to return to the -1 charge vacancy, thereby facilitating this rapid electron hole recombination cycle. Crucially, this prediction relies on the full complexity, i.e. the anharmonicity and metastability of the carrier capture behavior to be included, as the overall rate is essentially covered by the rate limiting step in the recombination cycle. So omitting either the tellurium dimer ground state structure or anharmonicity in the potential energy surfaces, or indeed the presence of metastable defect configurations, would break one of these rapid green links in this recombination cycle here, yielding slow charge capture behavior. Indeed, incorporating the effect of this non-radiative recombination cycle at cadmium vacancies into the calculation of the solar conversion efficiency using the trap-limited conversion efficiency metric developed by Sung Young Kim in Aaron Walsh's group, we find that the maximum achievable photovoltaic efficiency is reduced by over 5% from its detailed balance limit. These results help to explain much of the empirically observed behavior of cadmium vacancies, in particular the requirement for treatment strategies which passivate their deleterious effects. In fact, the 1 volt open circuit voltage threshold for cadmium telluride solar cells was recently broken by Burst et al., which required breaking the mold by shifting toward an unorthodox strategy of cadmium-rich stoichiometry and anion doping, reducing the formation of cadmium vacancies as well as tellurium and cadmium antisites. To conclude, we calculate a single deep negative U double acceptor level for the cadmium vacancy while reproducing the experimentally observed -1 hole polaron, finally reconciling theoretical predictions with experimental observations for this defect species. We find the cadmium vacancy facilitates rapid non-radiative recombination through a 3-step charge capture cycle, reducing maximum power conversion efficiency by over 5% for untreated cadmium telluride, a consequence of tellurium dimerization, metastable structural arrangements, and anharmonic potential energy surfaces. You can find the published version of this work here, and we are currently applying this same level of analysis to all intrinsic defect species in cadmium telluride before looking at the relevant extrinsic dopants, so watch this space. To end, I'd like to thank my mentors Aaron Walsh and David Scanlon and you for listening. Over and out.